So last time we were talking about mean, median and mode. And what they kind of tell us about, if you have some data, imagine the data like points. Mean, median, mode tell us something about the center. Quotation mark, center. So the mean, the median, the mode, and the midpoint, the averages, they tell us something about the center, where the center of the data is. So for example, a simple one would be like, if you had the data 2, 3, 5, 7, 12, 15, 18, the median is 7, which is literally the center if you rank them from, order them from smallest to biggest. So averages are good for giving us information about the center of the data, but what they can't tell us is this. So consider this data. Example. Hey Musharif, you didn't miss anything. This is the only thing I've written. So for example, so what I want you to do for me now, as a warm-up, neither of these have modes, so we won't ask for mode. The mid, yeah. Well, I'll say mode, but I know the answer is NA. So just to get us warmed up about one problem with averages, we can just calculate the mean, the median and mode for each of these. So I'll just put in a table A and B. No, it's getting us warmed up for a new idea. Okay. How are we doing here? Completed? What's the mean for A, Musharif? 7.94. Don't know about that. What did you get? That's what I was thinking.
7.
Yeah? Want to recalculate?
You can't all of this, no?
Yeah.
Why?
Yeah.
Why?
Because there's 3 of them. Huh?
A.
Yeah.
Oh, I am working.
Ah. No. These 2. Yeah. What did you get for the mean for B?
Yeah.
For B?
0.7.14. Oh, 3. But I kind of disregarded the 0.
Don't be doing that.
Yeah, 7.
7. Okay, the median? 7. 7. The mid? 7. 7. So, they look like the same, but they're actually quite different, because if you to draw this on a number line, this one here will be at 6, 7 and 8, but this one here will be at 0, 7 and 14. So this one, although they have all the same averages, they're two pretty different sets. So what is missing from our description is a way to describe how spread out the set is. Do you know, like how wide it is. Do you get what I mean by that? So can you see in the first set the numbers are close together, 6, 7, 8, but in the second set they're actually quite far apart, 0, 7, 14. So we'd like some way of measuring or saying how spread out the numbers are. The word is how, I don't know if you know this word, how dispersed they are. Unlikely. Do you know clustered? Yeah. Dispersed is the opposite of clustered. So the first set is clustered, close together, and the second one is dispersed. Yeah. So, how could we measure, if we got any ideas, how could we measure how spread out a set is? Well, what could we use to describe it? Well, some ideas could be, you could measure the biggest one minus the smallest one, kind of get a length like that. And that's actually okay. But there is another way, which I'll show you with an example. Let's have 5 numbers. Let's say, I don't know, 0, 5, 10, 15, 20, and 35. What's the red? Something like this. Yeah. The mean average here, I can calculate quite quickly. The mean average is 10. 10. Okay. Now, let's write a little column here. We'll call it delta for the moment. If we picture it like this, the mean is in the middle, 10. How far away are the data points from the mean? Well, the first one is, if the mean is 10, the first one is 10 units away. The second one, how far away is it? 5 units. The next one is at the mean, so it's 0 away, 5 and 10. Let's average these numbers. 15, 30 divided by 5, 6. So, what does that 6 represent? If you think about what you've just done, how would you describe what the 6 represents here?
The length, the average of the length.
Go on, you're on the right track, yeah. The average of the length between, or specify a bit more at the very end there, between what points?
10 and 2.
10 and? Yes, that's what this one represents, but what does this one represent? You're very close to it, and you've got the right idea. So what it is this is the average distance between the mean and all the points. So if you were to look at this distance, this distance, this distance, and this distance, the average is 6. So it's like you're saying, okay, here are my points, and on average they're about 6 away from the center, on average. Now of course, some of them will be more and some of them will be less, but on average it's 6. So you might think, okay, well, if the average is 6, then you can say roughly the total length should be twice this, because we picture the average as being somewhere in the middle. So if we multiply this by 2, we should have roughly the total length. So 6 times 2 is 12. So the centre is 10. If we add 12, that brings us to 22. And if we subtract 12, that brings us to minus 2. Now if you look at that and compare it with, one sec, this and this, you realise, hey, that's not too bad, not too far. Yeah? Question?
How did you get 22 on minus
6 times 2.
12?
Yeah, plus 10. And minus. Plus and minus 12. On the centre. That's something we'll come back to in the next chapter. But it's just a way of sort of kind of roughly checking that your answer makes sense. You know, if you think about it, if you have a list of data and you have the average, then the average distance from the average should be about half the total distance, roughly. Now, you might think, great, we have a way to measure how spread out the data is, but there is a small problem with this formula. The problem is the actual formula has something in it which I think we've talked about. So the formula is the average, which I'll use a little bar to mean average, so in this case that's a 6, minus each data point, so in this case that was 0, 5, 10, 15 and 20. Add them all up and then divide by, in this case, 5. That's the formula we used, and that's fine, but the problem in maths is we don't like formulas that have this in it. Have we talked about this vertical? Absolute, yeah. We don't like it. There's many reasons we don't like it. One of the reasons which you'll understand is because in maths we actually don't have a derivative for this. If I give you this function and ask you for the derivative, there isn't one. So this is one of the reasons we don't use this formula, but there's actually other reasons as well. This is just the simplest one I can give you. So the question is, alright, is there another formula we can use that doesn't have this in it, but is at least roughly the same as this? And the answer is yes. So I'll give you the formula, we'll calculate the answer, and see how close it was to what we just did a moment ago. So the formula is this rather ugly looking thing. Sum with a big square root all over n, the average minus the average minus the data squared. Okay, let's test it out. So big square root all over, what was it, 5, wasn't it? And the first one is 0 minus 5 squared plus, no, the average was 10, wasn't it?
10.
Yeah, sorry, yeah. 0 minus 10 squared plus 5 minus 10 squared. Was it 5 or 6?
No, there were 5 numbers.
There was 5 numbers? Okay. 10 minus 10 squared plus 15 minus 10 squared plus 20 minus 10 squared. Okay, let's calculate that in our head. That'll be 100 plus 25 plus 0 plus 25 plus 100 over 5. Okay, so that's 50, 250 over 5 is that it? 100, 250 over 5 is 50. The square root of 50 is about 7.1, something like that. What? 7.07. Okay. Now, I know that's not exactly the same as what we got previously. Previously we got 6. It's not too bad. And the good news is, the bigger your data set is, well, by that I mean the more points you have, the closer it is, yeah. So, although this formula looks a bit strange, it's kind of given us the same answer as what we got a moment ago, but it has much more useful maths properties. And we'll use this as a way to measure how spread out the data is, and it's called the standard deviation. And it's a way to measure what we call spread. how spread out the data is. So in other words, the bigger this is, the more spread out the data is, the smaller it is, the less. And what if it was 0? What might that mean?
There's only the mean,
No, go on, yeah.
um,
You have it essentially, yeah. What do you mean?
there's only the mean average, and there are no spread.
That's it. Everything is the mean average. So it'd be like, in this case, it'd be like 10, 10, 10, 10, 10. So in other words, all the data is constant. This, of course, can never be negative because of the square root. So it's a number from 0 to infinity. Could be 0. Could it be infinity? Not really. It's a measure of spread. And remember, roughly 2 of these is the width left and right of the data. Roughly.
Say that again,
Roughly 2 of these is the width of the data left and right. Now, this might kind of seem familiar to you in physics, because remember when we were calculating uncertainty, at the very end we had a plus minus part. In fact, what you didn't realize at the time was you were doing plus minus one of these. But I hope you can realize now that it would have been more accurate to do 2 of them because of what we just discussed. But the reason I didn't do 2 is because 2 of them would have been too big, and you would have had too big of an error. Because you didn't have enough data points, because it's only a small classroom experiment, so we just used 1 of them. Okay, so this is the formula for standard deviation, and we'll look at a couple of more calculation examples now. I'll scroll down. Is this Musharif? Enough? Yes? Okay, not yet. Any assignments due today? Just yesterday? Yeah? Okay. Can I scroll down a little bit? Yeah. Let's try one. And then we'll look at more difficult ones. So we'll just do we'll have 6 numbers. But we might they're not so easy. Okay. So I'll do this now in a moment. I want you to try. So firstly, you need to calculate the mean. And then secondly, you need to calculate the standard deviation.
The name of the system is standard.
Yeah, I should have said that at the start, shouldn't I? Standard deviation. Now, just so you know, I use this for average, but if you want the Greek letter, do you know which Greek letter is for average? Mu for average, sigma for standard deviation. Finished it yet? Yeah? Miss Sharif?
No.
Not yet? Okay. Okay. Nearly, huh? Yeah? Right. First, the mean. 0 plus 5 plus 2 plus 1 minus 2 minus 3 all over 1, 2, 3, 4, 5, 6. So I can see at least I don't have to put that, oops, that with that. So that's 6 minus 3 is 3 over 6 is 0.5 or a half.
Yeah.
So now the standard deviation will be square root. All the halves, yeah. 0 minus a half squared plus 5 minus a half squared plus 2 minus a half squared plus 1 minus a half squared plus minus 2 minus a half squared plus minus 3 minus a half squared. So that will be, and that would be so that's a quarter. 5 minus a half is 4.5, which is 9 over 2. Squared is 81 over 4. That's 3 over 2. Squared is 9 over 4. That's 1 over 2. Squared is a quarter. That's minus 2 minus a half is minus 5 over 2. Squared is 25 over 4. And then it's minus 3 minus a half is minus 3 and a half, which is minus 7 over 2, which is plus 49 over 4. So I need to add these all up. (166 over 4 over 6), and then square root the answer. 2.63. 2.63.
That's what you get.
That's not what you got? Or you did get it?
No.
You know what the problem is? Calculator.
No,
But it's too difficult. Look at it. Makes me so sad when I see it. I feel so bad for you. Huh? Okay, you have this?
Yes.
Yep. Let's do one now with a frequency table in it. Scrolling down. So I won't put as much in it this time. We'll just have 3 boxes. X and F. And we'll say -1, 0, 1. And we'll go with 3, 2, 3. So what I'm saying here is I have -1, -1, -1, 0, 0, 1, 1, 1. That's my data. Listen carefully. Listen. What I'm saying is I have -1, -1, -1, 0, 0, 1, 1, 1. That's my data.
3 minus 1 is 2, 0.
Exactly. Exactly. You don't, I don't know. Is that Musharif's happy face I understand, or happy face I'm confused?
No, it's okay.
It's happy you understand it face. Okay. So, let's try and do this one. I'll give you a moment. My goodness, I keep so tired. Deviation, is it DE or DI? DE. D.
I don't know.
No. It is DE.
Yes.
Oh, yeah, of course. Deviation. That's deviation.
Actually,
Was it? Deviation?
I will need your help
What?
in the speaking presentation.
What are you doing?
I want to talk about physics, mechanics.
Okay.
The conservation of energy. and
That's
the-
great. We can do a practice presentation in class.
Yeah.
Yeah. What are you doing?
Wave.
We can do a practice in class. Do you know what the other 2 guys are doing?
No.
Do you know if it's physics even, or if it's chemistry?
I'm not sure. Well, maybe probably do electric like last time, but I didn't ask.
Thank you.
I didn't ask
Okay.
them.
We can have a practice in class. Okay, try this one, and I'll do it now in a moment. The mean and the standard deviation. Once you have the mean, tell me what you've got, so I can make sure it's going okay.
Zero.
Correct, yes. Yeah. No, I did that on purpose to make the next one a bit easier. So the formula EAD that you're using is going to look something like this. Sum the frequency times the data over total frequency. Isn't it like minus 1 times 3 plus 0 times 2 plus 1 times 3 all over? Yes, which is 3 plus 2 plus 3.
The mean is minus 1 plus minus 1 plus minus 1 plus.
Oh no, don't do it this way. That'll take forever. Use multiplication. Minus 1 plus minus 1 plus minus 1 is the same as 3 times minus 1.
And this is, that's what it's this.
Oh, it's more than okay. It's great. Did you get the mean?
Yeah, 0.
Very good. So you're right, 0. Now on to standard deviation.
Yeah, the n is 8.
What?
Just 6 or 8.
The standard deviation should be quite small. I was definitely expecting a number less than 1.
Yeah.
Yeah? Because yeah, think about it. The furthest this data goes out is minus 1 to 1. So the standard deviation couldn't possibly be more than 1.
Yeah.
What? English, please.
Oh.
Kite?
Okay.
No, okay. What is it?
Something went wrong there for sure. What did you get? Make sure you-
1 8.
0.8 sounds reasonable.
Okay, what is it? Square root.
Square root.
Let's have a look
Minus
now.
1 plus minus 1.
Let's have a
Plus
look.
minus 1 all square. I mean minus 1 square.
Hang on. Let's have a look. Okay, so the very first thing we absolutely know is that it must be all over 8. We know this
Yeah.
because there's 8 points. Now the first one is minus 1 minus 0. So I won't bother writing the 0 in. I'll just write minus 1 if that's okay. Squared. But how many of those do you have? 3 of them. Plus 2, 0 squared, plus 3, 1 squared.
I don't know anything.
Yeah, what was it?
Right. I put the 3 and the 2 inside.
Classic EAD.
Yeah, I know, right? I know.
Alright, let's see. On the top, we have 3 plus 2 plus 3 over 8.
No, 2 more.
Sorry, 3 plus 0 plus 3 over 8. Which is root 6 over 8. Which is root 3 over 4. And root 0.75 is about 0.8, is it? Yeah. Don't know, the more than that, 0.87.
Yeah, that's okay.
Yeah.
Yeah, okay, good. Okay, this one's okay? Yeah. Now, this isn't really a big deal in the exam. In fact, I'm 99%, but not 100%, 99% sure they won't even ask you to do this on the exam, which I don't know if that's good or bad news.
Good, bad. Bad.
Is which good or bad news?
Bad news.
Why?
Because this is bad.
Easy.
Yeah.
Which is why I think they won't ask you. Yeah. But anyways, we'll just practice. So if you want, you can take a break for a couple of minutes. But I just want you to do 2 of them when you come back. So number 3 and 4, and that will be more than enough. And then we'll go on to the next lesson. Okay. So do you need to take a break, or what's the deal? Yeah. All right. So when you come back, we'll have a look at 3 and 4 then.